Hi, Reliable Web Summit. I am Fernando Alvarez, and I'm really excited to be talking to you about how to refactor JavaScript with some functional programming patterns. So let's go right into the talk. So today we'll be talking about maintainable JavaScript with functional patterns, or in other words, how to leverage functional programming to just improve your general experience with JavaScript and to reduce bugs, which is always great. So just introducing myself, my name is Luis Fernando Alvarez. I'm a developer at Stack Builders. We are a consultancy that focuses on functional programming and purely functional languages overall, but we take a bunch of other projects as well, and we try to put a functional spin-off on them just because there are some super clear benefits of functional programming and how they improve your code, even if your language is not purely functional. And we're going to talk about what being functional means through this talk as well. I am a musician as well, a bit amateur musician. I am married. I'm a father of 2 and 1 cat, should I add. And I usually spend my spare time learning dad jokes, and I'm kind of known in the office for that. I speak some languages besides Spanish and English. I'm a native Spanish speaker, and then I speak a bit of English, I'd say. and I speak all of those programming languages, and you can follow me on social media on those accounts. So first of all, I would say that I was born in 1985, where Back to the Future happens, right? And this is one of my favorite movies of all time. And in the movie, they visit a lot of years, right? 1985, 1955, 2015, and 1885. And the characters in the movie just take a lot of decisions, and that obviously affects the timeline. And when Marty goes from 1985 to visit their parents in 1955, he just does a lot of things that alter the future, right? For him and for everyone, really. And this is what kind of we don't want in programming, right? We just want predictable software that doesn't change with some external state. When we change some external state, our function resolution shouldn't change. And we're gonna go back to 1985, and here's the problem, right? That is not the same 1985 that Marty left. There were so many side effects, and no one would be able to predict what happened until they came back, right? So just a little analogy here on what we want to achieve with our language and with our languages, right? With our programs, and how do we want them to behave over time. And the truth of it is that we still do old JavaScript. And the language has some modern core features that we can leverage over time, and we can put into our code, and not just I'm not saying go and refactor all of your code, all of your JavaScript code, because that is very time consuming, and it doesn't make sense for bigger code bases. But we can go incrementally and just apply some of these concepts to little parts of our code, and we will see immediate gains. And why is all JavaScript so hard to maintain? That is kind of the main question here. And I'm doing a list here, and I'm going to go over these points as well. So we have a lot of for loops with common patterns, really common patterns. We're going to see some, for example, initialize, iterate over an array, and then push to a temporary array, and just to do things, to do accumulation, or to do list transformation, or whatever you want to do with JavaScript, either in the backend or the frontend, right? And in some code bases, we've seen big functions with a lot of switch statements. So it's a function, a really huge function that does a lot of things. And this kind of breaks in object-oriented programming. You have the solid principles, and you have the S, which stands for single responsibility. And some of it applies to JavaScript as well, because we want our functions to be able to do just one thing and do it well. And we also have a lot of nested if statements in most of the code, and this is bad because it adds to the cognitive load of the developer. If you're reading that code, you have to do a lot of thinking to just go deep into the if statements, right? And we're going to see how to refactor that as well with JavaScript. We have a lot of variable mutation, and that is kind of making an analogy to what I said before, right? About back to a feature. If we mutate our state and we make our functions dependable on that state, then the functions are not going to be predictable. And we see an abuse of global scope. So JavaScript has the var keyword that lets you initialize a variable, and a lot of code bases abuse that. They put things in the global scope, and they reuse them later just because it's easier, or it's I don't know. It's really the shortest way to achieve something, right? But it's not at all maintainable, and it brings more problems than you would avoid. So this is kind of the introduction. So we are going to see the functional side of JavaScript now, which you've come to see that is really, really good. And as I said, you don't have to do this on your whole code base. If you start small, then it's good as well. So we're gonna go into some basic functional programming concepts, right? Because it's a different paradigm of about what we're used to do in normal programming, right? Let's call it declarative programming, right, for now. And as the name implies, functional programming is function-based. So we do a lot of interesting things with functions, and there's a lot of them. Everything we are going to treat as a small composable function instead of having big and inflexible ones, as I pointed out earlier in the switch example, right? But these functions are not just any function. They have to have have to be pure functions. What do I mean with purity? These functions don't have side effects, so they don't affect the external state or get affected by the external state. So they are contained kind of in their own world. And there's another concept, a big one, that is immutability. And everything that we define in functional programming is going to be a constant. And nothing is going to get mutated through the program's execution. And with mutated, I mean changed. If you say that a variable is 1, then you can't change that value to 2 after in your code, right? And we're going to see the benefits, and we're going to see how to do this, because this is kind of the biggest leap from the usual way we do programming. So let's talk about purity first. So the functions live in their own isolated scope, and that's the idea behind pure functions. They don't, or they shouldn't, get affected by external state or affected themselves, right? And for this, they are really predictable, and this is the consequence. They have the same output every time they're executed, given the same input, right? We can see the kind of the example. Remember our algebra classes where you were asked to, I don't know, draw a function or just have a function there. So we have a function that is dependent on x, on the x value, and if you give a particular number to that function, then it would get a particular output. And there's no way that you could give that function the same input and get a different output. And this is called referential transparency in functional programming, which means you can virtually switch the function execution with its value, just because you know that it's going to be predictable and you know that it's not going to change over time. And these functions are deterministic, and testing them becomes really easy since they are really predictable, and they always return the same set of values, right? Based on the input, obviously. So let's compare these two functions. So let's have our line function, which is the same function that we saw on the last slide, right? 2x plus 3. And this is just a line. And in the left example, this is a pure function just because you're passing an x parameter to the function, and then you are returning the output based on that value. And you can see on lines, on the first execution of line function, you get an output of 7 if you give an input of 2. And then you give an input of 3 and get an output of 9. And if you execute it one more time, you get you can give it an input of 2 and return an output of 7, which is the same as the first call. So we know that if we call it with 2, it's going to give 7 as an output always, just because it doesn't depend on anything else but the value of x, right? Which is how it should work. But we have the impure version of it. So let's imagine that we define var, that we define a variable x in the outside scope, in the global scope, and then we read that scope, that global variable from the line function. This is going to be risky because if we change that x externally, we are going to get different values on the execution of that function. And we see a lot of this in actual production code from clients. And this is dangerous, obviously, because line function will behave differently for different times in the execution of the program, right? So, talking about this function, this accumulate function, right? Is this pure or impure? I would say that it's pure, just because it doesn't depend on any outside state. It doesn't have any side effects. It doesn't affect anything outside of the function. You get an input, you accumulate those values, and you return an array. But in this case, it doesn't matter. What bothers me in this function is the for loop, and you'll see why. Because this function is easy enough to read, but if you do something like this, which is a lot of nested for loops, you have to carry in your mind a lot of things, right, to just understand what its function is doing. I know this is a pretty trivial example probably, but we also see this, a lot of for loops and mutation and conditionals inside the for loops that depend on the values of the indexes of the arrays. We are going to have different outputs. So there are other problems with the previous two, and it's not just that they're not pure, right? We have seen that they're pure, and we see that the main problem here is that we have to track the variables that we use to track indexes of those arrays, the accumulator value, which is what gets added and mutated on each iteration, and also there's a comparison between j and k in one of the parts of that code, and this feeds the cognitive load. Cognitive load is just a psychology term, just that says that you can only track so much things in your brain at a certain point in time, and if cognitive load is large for a function, our brains can't keep track of everything. Our brains have short-term memory and are very fragile, right? And I don't remember what I just added in the function, and what value would it take, what value would I or j or k will take in my function. So this is kind of the biggest problem in these. And in essence, we are telling the computer, when we do a for loop, we are telling the computer how to do its job. The computer should know how to iterate over a list of elements. I shouldn't tell the computer, hey, point to the first element, then operate on that element, and then move to the next element, and be careful, because we are going to stop at the last part of the array, at the last element of the array, and not go one element further, because that will give us an error, right? But the computer should know this. I shouldn't tell the computer that it shouldn't go over a list of elements, right? So this is kind of the bigger problem with for loops, that we are telling the computer what or how to do its job instead of what to do. We don't give the clear instruction, but we deal with a lot of lower level things that the computer should know how to do. And we're gonna switch a bit to immutability, and we're gonna go over this way of telling the computer what to do instead of how to do it, and we're gonna go over it later. But let's talk about immutability first. So once a variable is defined, it can't be changed through the execution of the program. And in other languages, they are thread safe, right? If we define every variable as immutable, if we define everything as a constant, that makes them thread safe, just because you can't alter those between each thread. In JavaScript, since it's single threaded, we don't have this problem a lot. But for this reason, they provide an additional level of security. And immutability, in essence, it means that for the rest of this presentation, we are not going to use the var keyword, which we still see in production code. And also, we are going to stop using let. And you'll say that is kind of weird, right? How am I going to do some basic things if I don't have variables that I have to mutate? And we're going to go over that. But we are only using const to define our variables, or let's call them constants, right? Because const is to define a constant. But about const, let's talk about it a little bit. So const, what it does, it is disable reassignment on a variable, on a structure, right? So we have name, Marty McFly there, and then we try to set that name to Dr. Emmett Brown, and that is not allowed when you use const, just because you are telling to just disable the reassignment. And it's possible to change with objects. It works a little bit different, because it is possible to change the properties of the object. Let's see this line that says bad guy Biff Tannen, right? First name Biff, last name Tannen. If I try to change the first name, it would let me change that, because in JavaScript, objects are not stored in the variable, just references to that object. So the actual value in bad guy is the reference to the object that holds Biff and Tannen, right? But if I want to assign a new object to that to a new reference, or a new, in this case, a new object reference to that variable, I can't do that. Just because I would be changing the pointer to another object. But how do I do things without mutation? And that's kind of the biggest question, and that's what I struggled with, right? Because before going into functional programming, just because I had my brain fixed into, you need variables, you need to change things for it to work. And it's about copying things, copying structures or copying data, and not modifying the original data. So in the first example, we can see that we create a bad guy object, Biff Tannen, like before, and then we say other bad guy equals bad guy. This is not a copy. What I'm saying here is just the other bad guy constant is going to hold a reference to bad guy. So this is not copying the array. This is just referencing the same memory address, right? And we can use the rest and spread syntax in JavaScript, which are the three little dots that you see there. And essentially, what I'm saying in the second example, I say same bad guy equals, and what I'm doing is just copying all of the properties of bad guy and adding that to that object, right? And I can also copy only certain properties. So I have bad guy 2, and I am gonna copy all of the properties from bad guy, and I'm gonna modify, or I'm gonna just not modify because I'm creating the object right now, but I'm setting the first name attribute as Griff instead of Biff, right? And this also works with arrays. So we have an array of years below there. And if I want to copy those, I could just put the array syntax and then ... years inside it. And I would get all of those in a new array. You can do that with array concatenation as well. And this is one of the benefits of the REST and spread syntax, that you can do some of these things so much faster than it's very, very good. In the all years array, I'm just going to copy all of the years array and add a new one, right? Same as concatenating two arrays. So we've seen purity and we've seen immutability, right? Right now we are going to talk about functions in JS, and functional programming relies heavily on functions, as I told you. And there are two concepts that are key in functional programming. So functions have to be first-class citizens, and in JS they are. And this means they can be assigned to variables and treated equally as any other variable, right? They can be reassigned, they can be put into an array, or they can be put into an object, or whatever you want to do. So we can see a simple example here. So we have an add2 variable, or constant in this case, that holds an arrow function that says, if I get a value of x, I'm going to add 2 to that value of x. That is what that arrow function does. So I can then call that variable, that add2 variable, with the argument, because the add2 is going to resolve into a function, and then the function needs some arguments to operate. So I'm gonna be able to do that. And also in JavaScript, functions are higher order functions, which means that they can either be passed as arguments or returned from other functions, from the execution of other functions. So we can see that function called doTwice here, which receives an operation argument and returns a new function. And that function receives number and returns this thing that we see here, right? 2 times, doing the operation 2 times, and receiving the argument from the inner function. So this, we can see how this works here. We call doTwice, which resolves into a function. So we have to pass one parameter to it, and the parameter is the operation in this case. And we are going to pass the add2 function that we defined on top of the previous example, right? And then I'm going to say I'm adding 2 to what? To the second argument or not the second argument of that function, but the argument to the function that gets returned from the first one. And this is kind of confusing right now, and you will say, oh, it just makes everything more complex. But we're going to see a few examples that will let you understand this better. So in JavaScript and in most languages, I would say, the most popular application of higher order functions and the functions where we use a function argument the most are map, filter, and reduce, which are essentially used to do transformations. But you can combine them, mix and match them, just to do a bunch of things that we are gonna check. And those things that you see below the functions, if you are not familiar with them, they're called the function signatures. And you can read them as just a list of arguments, and in the end you have the return value of the functions, the return type of the functions. So what map is saying to us is we receive a list of elements of type A and a function that converts A into B, type A into type B, and then an array of type B gets returned. You use this when you want to retrieve, for example, when you have an element of an array of 5 elements, and then you want to transform it into an array of 5 other elements. For example, you would want to, I don't know, transform strings to numbers, or just you have a list of strings and you want to count every one of the strings and store that in an array. Then you do a transformation from a string to a number. And filter, this is the second function that we have. And what it does is receives a list of elements of type A, and then a function that transforms those A elements into a boolean. And these functions are what we call predicate functions. The predicates are functions that return either true or false, a boolean value. And as you can see, filter returns a list of elements of type A as well. So what it implies, it's that we are gonna get a list of elements and then filter out those elements if they fulfill a certain condition given by the function that you pass as the second argument, and then it's going to return a list of elements of type A, which has either the same size of the original list or is a subset of the original list. you can't add new values to the list with filter, just remove elements, right? And then you have reduce, which we're going to see it applied in a lot of places. And this is kind of a bit more complex. It receives a list of elements of type A, and then it receives a function that we usually call the reducer. The reducer, what it does is gives you an accumulator. We are going to see that clearly in the examples. It's an accumulator and a value. And what it does is play with those two values and return a value of type of the accumulator. And then the third argument for reduce is usually the initial value of the accumulator. And in the final, after the final arrow, we can see that it's of type B, which is the same type of the accumulator and the initial value of the accumulator. So what we can say about reduce, I usually see it like reduce. What it does is receives a list and then it squashes that list into something else. It could be the same list. It could be an object. It could be, I don't know, a boolean in the end. And we're going to see a lot of different applications for reduce that we can do a bunch of things with it. We can even implement map and filter using reduce, and that's the beauty of it. And as I mentioned, reduce can be used for several things: accumulators, word counters, string joining, and even implementing map and filter with it. But my favorite thing that you can do with reduce in JavaScript is function composition. And I told you about having a bunch of different little functions that do, every one of these functions does a little thing. And these can be combined and these can be composed. This is what we call function composition. And we can build new functions out of the old functions, right? Out of the little functions, we can build bigger functions that help us transform something or operate on something. And I'm not going to go deep into this code, but in essence, what it does is I receive a list of functions in compose. It's just a list of arguments, which are functions, each one of them. And then I reduce those functions and I apply those functions in sequence to every one of the array values given by args, right? We are going to see an application of that function and see how it works in the real world. This is kind of confusing right now. If I think it's confusing at least, but we're going to see the examples here. So based on what we have learned, let's look at some actual refactoring patterns and how we can use these higher order functions just to do a bunch of amazing things. So let's jump right into the code. Great, here's the code. So our first example, we are going to call initialize, iterate, push pattern. And what in essence it does is what we see on the left, right? We have a list of words and we initialize a temporary array, which we're going to call capitalized right now. We just initialize it to an empty value. Then we go and iterate over each of the words and then push to our temporary array, right? With whatever we want to do. And this is super common. You're going to see this in a lot of places. And you're going to see also that people use for each in the original word array. And this is not really functional, right? Because we are mutating the capitalized variable. And we are digging deep into the indexes of that array with a for loop. We have to take, have a track of that when we execute this function. So refactoring that functionally, we are going to see the second example on the right. We have the same list of words, and then we are going to expose a function called uppercase. We are defining that function in line 2. This function is going to receive a word and then return that word in uppercase, right? And then we are going to use the map function as I told you before. And we don't need to iterate over anything because map knows that it should go from the first to the last element. here and execute the uppercase function on each of those elements. And you see that it's only 3 lines versus 7 lines here. And maybe I'm exaggerating a bit on the left one because we can definitely improve on that. But the functional approach is really what it makes it really concise and really understandable. And a good thing is that we can use that uppercase function in another different algorithm later. And yeah, it's very convenient to test or to compose. We're gonna see in a bit. So right now we can see another implementation or another application of the map function. Sometimes we have an object, and what we want to do is transform that object into an array. For example, we have this object, and we want to export that as a CSV. So we want to put it in an array format first, and then use our library for CSV to just put that into a file, right? And in the left example, we are doing something similar. We are going to take out the entries of that object and iterate over them, and then push that to an array that we are calling flat array in that example, right? And it's still the same. We are mutating flat array, and we are having a for loop here. And we can refactor that by using a map as well, because what we want to do is just go over each one of the keys of that object and put that into an array. On line 7, we can see it's exactly the same as line 8 in the first example, which I'm taking just the object entries, and this gives me a bidimensional array that has each element has the key and the value of that object. So I'm going to create a function that is called extract value, which receives this array, and I destructure that array. That is another one of the really nice things in JavaScript, that you can destructure things. And I'm just going to return the value or the second element from each one of those array values, right? Which are arrays of 2 elements. And in line 9, what I'm doing is just going over each of those entries, each of those traveler array entries, and extracting the first value. So this would receive that list of entries and then return just the values of the object. So our second really common pattern, we are going to call that initialize, iterate, and conditional push. It's very similar to the previous one, but as you can see in line 6, you don't push every one of the elements. You just do a conditional one. In this case, we have a list of words as the other example, and we have an array that says long words. I'm just gonna accumulate or just put. I just want to know which one of these words are longer than 5 characters. In this case, would be Marty and Einstein, right? And if we do that in a for loop, we have to do just what you see there. In line 6, we are gonna conditionally push to that long words array, depending on if the word length is greater or equal to 5. And we can refactor that using a filter, because if you analyze what we are getting just a subset of the original words array. So in our second example, we have the same word array, and then we are gonna define a function, right? A function that we are gonna call larger than. And larger than is a function that receives a number, and then that function that we return from the first one is gonna receive a word and tell me if the word length is bigger than the number that I've given it. So one of the big concepts in functional programming is currying, and currying is just decomposing a function with multiple arguments into several different functions with one argument, and that helps us compose those functions. So as you can see in line 6, I'm going to define a function there that is called larger than 5. And I'm going to use the larger than function that I created before, and I'm going to give that function an argument of 5, right? So this is what also what tied to something that we call partial application, right? Which is having a function with many arguments, but I'm just going to give some of those arguments to the function, pass some of those arguments to the function, and leave one argument unapplied. And that result kind of store that, I'm going to store that little function with a missing argument in another function. So I can just reuse them. And this is what's happening here. I use the larger than function, passing an argument of 5 here, and assigning that to a more readable value that is in this case called larger than 5. So I know when I apply something to that function, it's going to tell me if it's larger than 5. I could have a function here that says larger than 10. And I've essentially reused my larger than function for different use cases, right? But in essence, this is doing the same as the left example, right? I am using I have a long words element, and I am filtering the words in the original array, passing the larger than 5 function to it, just to cut off all of the values that have less than 5 characters. So filter helps us do a bunch of really nice things. We in this example, what we want to do is just keep the true values and later count them, or do whatever we want to do with that resulting array. So in this case, we are pushing into the true values list conditionally, right? Similar to what we did before. And we saw that we can solve that using a filter. And as you can see in the second example, is really concise. You just have the all values list, and then you have true values. And what you're doing is just passing the boolean function, the function that converts anything to a boolean. And since it's a function, it's going to return true or false. And in this case, it's going to help us filter that array of true and false values. So I'm going to just keep the true values, just because the boolean function is the one that satisfies true for all of those true values. And this is a pretty nifty trick. And you can do this not only with boolean values initially, but with values that evaluate to boolean and are truthy or falsy. So we're going to see another super interesting pattern that is called initialize, iterate, accumulate. And you see this everywhere. You initialize something and you want to accumulate some values in an array, or you want to squash some words into a sentence, or there's a bunch of applications here. Right now, this example, what it does is we have a words array with the DeLorean, and we want to just accumulate those values into one. We want to squash those two words into one, because DeLorean is just one word. So what we would do is just and DeLorean is lowercase right now. So we are gonna do a camel case on those two words, right? Join them, but in camel case. So what we can do here is just extract the first character, take it to uppercase, and then extract the last characters with slice, as we can see in line 7, and then join those, and then mutate the camel case variable to just append something to that text that we have there. So the output of this would be Marty and his DeLorean, and yeah, this is a kind of a good way to do it, right? But we still have mutation and we have the for. And on the second example on the right, we have the same thing, but extracted into functions, right? So we have a function that is called camel word, which what it does is what we are doing in line 6 and 7 here. In line 3, we are gonna extract the first character of the word I give to that function, take it to uppercase, and then append all of those, all the rest of the letters of the word, right? And then I want to do a camel sentence function, which receives a sentence and a word, right? And this function, what it would do is just concatenate the previous state, or the previous accumulation of that sentence, and append the word that we are gonna pass it, right? And we're gonna use the camel word and that word just so it gives me the same output. So what I'm doing is using a reduce here. Remember that reduce can be used for anything else that is not covered by the other cases. And as I told you, reduce can be is so general that it can be used to implement a filter and a map. Just ways of doing things to implement those two functions. So what I'm giving the reduce function is the reducer, which in this case is my camel sentence function, which combines words and then camelizes a word in that list and just pastes it over some accumulator. And the second argument to reduce in this case is the same initial value that I have in line 3 in the previous example. So it's Marty and his, and then I'm going to reduce everything, reduce all of the words in the words array, and append to that sentence. So you can do reduces for almost anything really, and we're going to see a bunch of examples for that. So as I told you, reduce can be used to squash or to reduce an object of any form. The output of reduce can be of any form, not just lists or subset of list or the same a list with the same number of elements from the original list, right? So I have an array here, a bidimensional array that has the evil guys in Back to the Future. And what I want to do is transform that array into a key value pair, right? Into an object. So what I'm doing in line 7 is defining an evil object. And then inside of the for, I'm just going to extract the key and the value from all of those elements and evil guys and mutate the object on line 7 to add to have the key and the value, right? And it's pretty simple, and we've seen this pattern everywhere. And we can do the same thing with reduce with just a smaller code, right? So we have defined in line 7 a reducer, and a reducer, as you remember, receives an accumulator and the current value of the iteration. And in this case, I'm destructuring this value. As you can see, is key value. I'm destructuring every one of those arrays of 2 elements because I know I want the key to be in the first element and the value is going to be in the second element. So what I'm returning from the reducer is just a new object, which is this one. So it's this object. And I'm going to just put all of the properties that I have in the accumulator at the top of the new object. Since I'm returning a new object, then there's no mutation. I'm just creating new structures on each iteration, and then I'm gonna add the key and the value that I want for that iteration. So what happens here is that when I run a reduce on evil guys on here, I pass the reducer, and on the first iteration, my object is empty. So the accumulator here for the first iteration, is going to be an empty object. So it's not going to accumulate. If I would put something like, I don't know, foo bar, that's the greatest example ever. If I put foo bar, then the first iteration or the first application of that reducer, when I'm standing in this element of the array, is going to have foo bar here. So it essentially would do something like foo bar and then the key and the value. But to keep it general, I'm going to just get the previous value of the accumulator and splitting it into the new object, right? And this would do essentially the same as we can do on the left side. And what I usually like to do in these cases is just adding these smaller helper functions into another file, into another place, and I can reuse those functions across different applications. and it's really handy because we're going to see in one of the next examples about composition, and we're going to see how we can use those functions to just build more complex things. So talking about reduce, and I'm starting to sound like a broken record here, but you can really reduce anything. We have reduced an array, we have reduced an object, and now we are going to reduce something else, right? And in the left example, I'm going to define just some smaller functions, add one, duplicate, and square. And if I want to calculate a value out of those three, I'm going to have to nest those calls, right? Square, duplicate, add one, and then pass the argument to one, and that's 16, if my math is correct. Or we can do the same with arrays, right? And we're gonna apply map into this one. It's not very typical, but I just wanted to save a bit of time. So I'm gonna map all of the numbers here in 1, 2, 3, and I'm gonna map them to the add one function. And the add one function, as you can see, it adds one to each element, and then this returns another array. And I can just string together most of these functions, map or filter or reduce. But if you have 10 functions in the calculation, it's going to be hard. In either this case where you would have to nest everything, or in this case where you would have to just keep a long list of calculations. So as I told you before, we can build a compose function out of reduce, and this essentially what it does is receives a list of functions, receives a bunch of arguments that are functions, and applies those to the elements, right? It kind of combines those functions into one. And its usage would be here. You're free to copy this code wherever. It's just the general implementation of compose, and we have the same add one, duplicate, and square functions here. But I'm going to build a new function called calculate. And calculate is going to be a function that is composed of add one, duplicate, and square. So when I want to apply this function to whatever I want, I can just do it. Calculate one, and it's going to give me the same values as the previous example, or I can map that calculate to my list of maps, to my list of numbers, sorry, and it's far more convenient than having super long lines. And I think this code looks larger. The second example looks larger just because I have the compose function here. But ideally, you would have this in a helper file and just reuse it wherever you want. And our final example is just a pattern that we see a lot in production code. And let's suppose we have a greet function that receives an action and a name, and you would just greet the person with their name, right? But it depends on the action. The output of the function would be different, and you would have a default case here, right, where you return this anything function with all this text, right? What are you doing? Because there's not a greeting. That's not a greeting, and we can leverage the concept of functions as first-class citizens, right? Because we can just assign those functions to everything, to arrays, to other functions. We can put them into objects as values of the object. I don't think you can put them as keys, but you can put them as values of an object. And this is exactly what we're leveraging here. So we are doing a greeting map in the second example, where we have our list of actions as the keys of the map, and we have our functions. And it's not the application of the function, it's the function, the actual function, as values of that greeting map. So when I just want to run the greet function, I shouldn't have to do that switch statement. I just go into the greeting map here, and I look for that action. And if it exists with this ternary operator, I can make this bigger with a more standard if condition. But let's do it like that for the example. And if it exists, I will just run. I'll just look up whatever I have in the greeting map for that action and pass my name argument to it, my name parameter here. and that would execute the function, the same as we are doing in the first example. And to model my default value, we just the else from the condition, right? And I would just run anything, which is my default function, passing the name here. And as you can see, this makes it a lot more scalable, just because it's just a matter of adding a new function here. Let's say night, and then I call a night function here, which obviously I don't have here, but I wouldn't have to change the greet function, just my greeting map. So summarizing, please use functional programming in your JavaScript code. It's going to make it a lot more maintainable, a lot easier to read. And start small, refactor. You can study a bit more, a few more concepts, and then repeat, and then combine it with a more traditional approach in JavaScript. You don't have to go full on into the functional world. And if you want to dig deeper into functional programming, there's some good entry libraries to explore before going into a more functional, purely functional language. You can do Lambda, JS, or Fantasyland, which are some really nice libraries to start exploring them deeper on some of these concepts. A thing that I would recommend to any JavaScript developer is just to not stay in JavaScript. Let's use TypeScript. TypeScript helps you reason your code a lot better when it has static typing, and it protects you from yourself. Really, you can just have the same type safety inside map structures or inside reduces, so you know exactly what you're getting as an input and you're getting what you're getting as an output, and you kind of constrain your functions to act the way you want them to act. And if you want to go deeper, there's this library called FPTS, which has a lot of concepts from functional programming and applied to TypeScript, right? With the strong type system. So go check that out. That is a really nice library. And with that, I'm saying goodbye. Happy refactoring on your code. And there's my email and there are my social networks. You can just follow me or ask me any questions that you have. Yeah, happy refactoring and have fun with JavaScript. Bye.
Hey, it's Joe Eames with ng-conf. If you like that video, be sure to click subscribe either here or here, somewhere over here. And if you're looking for something more, here's another video for you to watch here or there or somewhere.